Our speaker as a first speech. So Professor Ori Cheshnovsky. So he was graduated from Tel Aviv University, and he after his graduation with a bachelor and a PhD degree, he went to Harvard for postdoc research, and then he went back to have a full-time faculty position in Tel Aviv University. And in fact, he was kind of top experts in the field of electronic spectroscopy, and the technology he developed is now used as really standard methods in his field. And today, because we are going to focus on nanoscience technology, so you will hear a lot of nanoparticles, and Professor Ori will make it even more easy, which is called Restless Nanoparticles. So he leaves some secrets to me, but I will let him to introduce the very funny story about that.
Thank you. Due to some, I hope, temporary knee problem, I will sit down. I will have you sit down? Okay. Okay.
It's not friction, is it?
Yeah. I was going to ask Michael Urbach whether it was his knee or my knee on the screen, but it doesn't matter.
It was mine.
It was yours. Okay. So you'll have to excuse me, I'll sit down. And I'm very glad to be here today. And in a moment you'll hear why. While Professor Guangxi Zheng told you about history, I'll tell you a little bit about prehistory. Namely, I was 24 years ago. I was a young associate professor, and I was part of the first delegation, scientific delegation, that went to Beijing to form the first scientific relations between China and Israel. And in fact, at that time, there were no formal diplomatic relation. Actually, that was the first delegation whatsoever who came to China to exchange ideas and see ideas. So due to that, actually, most of my friends in the delegations are already retired. I'm the only one, and there's one guy in Jerusalem who still is, no, all of them are active, but who still has a position and is not alumni, emeritus, namely. So in this perspective, I'm very glad to be here today. It's overwhelming how much science have developed in both our countries. And I'm very glad to see that those scientific relations have matured into such a nice and exciting endeavor such as Xin. And for that, I would like to congratulate both Professor Guangxi Zheng and Michael Urbach for conceiving the idea and bringing it up and making it possible, and to Professor Yael Hanin and the counterparts in China whom I don't know yet. Again, you. Okay, very good. Who making this whole idea really mature and come true. It's a very nice endeavor, and congratulations to you all. So I'll talk today about restless nanoparticles. I made two scientific presentations, but I'll try to explain complicated slides in simpler terms, so I'm not aware that the audience will be so diversified. Anyway, first I will start with advertising the scientific topics on which I would like to cooperate with Tsinghua University. Two topics that have to do with spectroscopy and microscopy of the nano objects. One has to do with super resolution microscopy, namely to develop a method for which label-free, no dyes, will be able to see objects smaller than what regular macroscopy will allow. This field is vivid already for about 15 or 20 years, but always using dyes and fluorescence. And the idea that we are going to present, it's a Mark. Yeah, pointer. Okay. Yeah, well, probably that's what I do. But okay. Okay. So which one is that? Which one is the?
Somewhere hidden. I don't know where it is.
Okay.
Here we go.
Which one is? Which one is the marker? The top one?
Yeah, here we go. Here we go.
Okay. All right. But then I will have to go back. So the idea is that if you form with a laser some gradient of temperature on a sample, you can utilize the fact that properties of matter change with temperature to enhance resolution more than you would actually see with a regular microscope. And what you see here is some simulation that we have done which deal with the Raman spectroscopy of a sample. And we have shown that resolution can really be increased by a factor of 3 over what a regular the best microscope can do. And what you see here is utilizing the same idea with a phenomena which is called thermoreflection, namely that the temperature influences by how much a material reflects. And what you can see here is that one can see finer object with a thermoreflection than with regular best microscope you can achieve. So this is one topic. The other topic that I would be happy to cooperate with you guys, is to do with single molecule absorption. People have done for many years already the detection of single molecules by recording their fluorescence. But there are very few laboratories who knows how to check the light absorption of a single molecule. And we are one of the few laboratories which can do that. And the scientific goal is to see whether by putting a little bit of germanium into silicon nanorods, we can improve the absorption of light, and by that, in principle, make photovoltaic devices more efficient. And now to the subject of matter of the current presentation. It has to do with the fact that nanoparticles are expected, if they are prone to serve some technology, to be stable. And they are believed to be stable. You form a uniform distribution or single size of nanoparticle, then you hope and you believe that the properties are well defined. And what we have seen, well, at first we didn't like the idea at all, that the nanoparticles that we are checking are extremely unstable, and for some reasons that I will explain later, we can see that very obviously in bismuth nanoparticles. So now bismuth, the bulk material of bismuth is semi-metal, and it's highly anisotropic in its properties. Without going into the term of effective electron mass, I can tell you that in one direction and another direction, the conductivity properties can change by 2 orders of magnitude of a single crystal of such bulk metal. And those particles are also, they didn't make their mind exactly whether they are metal or non-metal, and that makes them very to single out in the properties. And in fact, if you form nanoparticles, they tend to be not semi-metal but semiconductors, and they are very highly non-isotropic as well. There are several theoretical predictions which tell you that such nanoparticles will be extremely good for thermovoltage technology. That nanoparticles made of bismuth are expected to have very high thermovoltage coefficient. Thermovoltage coefficient has to do with the fact that if you put some gradient of temperature on a material, voltage is developed between its two sizes, the hot and the cold one. And this is, in a way, considered to be a competing technology to optovoltaics devices like silicon that absorb light and turn it directly into electricity. Some other ideas tell you that in some specific condition one can concentrate the sunlight, make a spot hot, and form this difference of temperature into electricity. So this is a driving force for lots of research on thermovoltage in nanoparticles. And as I told you, theorists, and they're always right, mostly right, predict that the thermovoltage would be extremely high in such condition, and that's why we tried to measure, I'll tell you in a moment who, to measure the thermovoltage in bismuth nanoparticle. It turned out that they are completely restless. They don't have any uniform properties. It was very disappointing at the beginning, but in fact it turned out to be a very nice laboratory to learn about the fact that nanoparticles not necessarily represent uniform properties. So the fact that small particles, less than 1 nanometer, that have several atoms, several hundred atoms, are unstable has been known for about 20, 30 years, but it's the first time that one have observed that a particle which have 7 nanometer diameter, which contains many, many thousands of atoms, are still unstable. And that was first observed. In TEM pictures of such particles. It turns out that they are quite non-stable. This is a picture of the same nanoparticle, those 3 pictures, and in fact they form one form, and then they sort of like melt and form a sphere of melting particle, and then they form another form. And even in the periods where they are quite restful, don't move, if you really follow the picture, you can see that some atoms on the surface have moved quite a lot. So what we would like to do is to see whether we can learn about the property of such particles, not only from these pictures, but also by measuring directly properties of such nanoparticle. And the best tool to do that is to learn this particle under an STM. STM is a magic instrument by which you can put a needle of metal and resolve the properties of nanoparticles 1 atom at a time with such high resolution. And for that, in '86, the inventors have won the Nobel Prize in physics. And the added benefit of such an instrument that not only you can learn about the shape of this particle, but also learn about its electronic properties. So what you see here is those particles, the topographic image. But actually, what you can do is tell exactly whether such a particle is just a step in a gold surface or a nanoparticle. Because if you form a graph of the current through this particle versus the voltage, this is a typical behavior of a metal, a continuous change in the current, exactly like a resistor would do. And what you see in a semiconductor nanoparticle, that there is some region of small voltages when there is no change in the current, although which is 0, although they change in the voltage. And this is the fingerprint that this particle is semiconductor. So you want to know what is this and what is this. This is gold or a metal, and this is a semiconductor. So we set to learn the properties of such nanoparticles, and what we saw that when we record for a long time, we sit on a single nanoparticle, and we record for a long time the current that passes through it with a fixed voltage, then the current is very chaotic. It changes in orders of magnitude up and down. So this can signify two things. Either that we are extremely bad experimentalists, or the other possibility is that indeed that reflects the properties of the nanoparticle. To show you that we are considerably good experimentalists, you can see that if we make the same experiment on top of a gold surface, in this current is very stable. Actually, this is a fingerprint of a good apparatus. Actually, we have built this apparatus. It's very good, quite good. But as we stand on the other particles, we have very erratic changes in current. So it's not only that in the picture varies, but also the properties varies. But that can originate for two reasons. First, the particles R can roll and get closer or farther from this particular needle. And if that happens, also one would expect fluctuation in the current. But the other possibility is that indeed there are changes in the electronic properties of these particles. And to check that, we have to measure the band gap of the nanoparticles, namely this plateau that you see here. How this plateau changes with time. And if this plateau changes with time, that tells you that it's not a uniform particle which had moved, but actually there's some change in the intrinsic properties of this nanoparticle. So that's what we have checked, and indeed we have seen that as the current changes, also this plateau, which is called the band gap of a semiconductor, changes. So we have done lots of experiments on that, and that signifies or actually conclude probably more than half a year of three talented students with a conclusion that at 300 degrees the behavior is completely erratic, and as one cools the particle more and more, then the particle becomes much and much more stable and doesn't undergo such energy, such spontaneous properties changes a long time. In other words, the conclusion, band gap change spontaneously by thermal activation. They are very fast at room temperature and very slow at 80 degrees. Now one can control in a way the rate of these changes. If you coat the nanoparticles with different coating, protection layer, then those particles can slow down or accelerate this rate. One can see furthermore that not only that the particle change its properties, but if we record a particle in different location at very low temperature, where it's relatively stable, then on two different faces of this particle, one would observe two band gaps, like what you see here. You see one gap which is small and one gap which is wider. And then if we do the same experiment of another particle, the kind of particle that you use for dyes, they are stable. In other words, this is not a good candidate for thermovoltage. Those are particles which are extremely unstable. If there are band gap fluctuation, probably the chemical potential of this particle changes too. And then, since we were obliged to measure the thermovoltage, and that's what we did, then we have to see what's going on. Okay. So let me skip the way that we did the experiment. It's quite an elaborate and difficult experiment. In fact, it's the only experiment where people have measured thermovoltage on nanoparticles. People have measured on surfaces, on monolayer surfaces, on things like that, not on nanoparticles. But let's keep the experimental difficulty and just tell you that if you measure the thermovoltage on 2 flakes of platinum and gold, I think that's what you have here, platinum substrate and gold islands, then if you measure such a voltage, you have a very distinct value of thermovoltage for both surfaces, gold and platinum. However, if you do the same thing for bismuth nanoparticle at room temperature, then it's quite a hell. Then you see again very strong fluctuation. In other words, this is not a good candidate for technology. This is very chaotic particle. And again, if you compare the same measurement over a very long period of time, you see, yes, we know how to do these measurements. We get very reasonable value, very stable value that do not change in time, while the bismuth nanoparticle is still very erratic. I will not dwell much time on the details. I would like just to tell you we were quite disappointed and quite frustrated to see that. And then we have decided to do theory and to see what do we really see. And what we have seen that if one formulates the properties, the theoretical properties of those particles into the 2 different directions, indeed one could see different value of thermovoltages. And in other ways, what we see here is actually a single nanoparticle which change sort of simultaneously its direction of crystal in a spontaneous way in every conceivable angle. Because if we see, if we compare our experimental results, those are the red dots here or triangles, with the theoretical simulation, that should be the measurement of the thermovoltage, the distribution over all crystal direction, rather than a single nanoparticle with a single value of thermovoltage. What we have here is sort of thermodynamic ensemble of nanoparticles in one. Is it good? Not necessarily for technology, but it's very nice to see that one can probe properties of particles this way. And because bismuth nanoparticles are very sensitive to changes, this is sort of a warning sign for other nanoparticles in other technology. Even such large nanoparticles have tendency spontaneously to undergo changes. Make sure your technology and your nanoparticles do not do so. So that's the end of my story with the conclusions that bismuth nanoparticles exhibit mechanical and electronic structure transformation due to its shallow energy landscape. Namely, it's relatively easy to go between one form and another. And the electronic structure changes have been identified in the band gap and in thermovoltage. And that within a single nanoparticle, you can measure profound band gap anisotropy. And that this dynamics can, to some extent, be controlled by passivation layer. And that statistical analysis of thermovoltage is consistent with a complete ensemble of uniformly distributed bismuth nanoparticles. Thank you very much.
Thank you. Any quick question? One over here.
Okay, the implication is that the shallow landscape of bismuth is what makes it less stable.
It makes it less stable, and the fact that it's extremely anisotropic makes the phenomena very obvious to be measured.
Is there any correlation with the melting properties of bismuth versus gold?
Well, there is. You're right. It's
melts low temperature?
right, much more. I mean, like 300 degrees.
It's more like this.
Yeah.
You said there is a way to control it. You think it can be used as a memory device?
I won't throw away this laptop yet. No, I don't think. The fact that it's not, if you want memory, you would want well-defined bistability. Well, here you see this, the landscape of many energy levels. I won't go to this direction at all.
Okay. That's a question and next speaker.
I have a question. So you mentioned the bond gap will change with temperature. So I want to know the speed. How fast the bond gap changes with temperature?
It depends on temperature. In room temperature, it would be compared or faster than 30 milliseconds, because we have observed that sometimes at room temperature, within the measurement itself, the band gap changes. At 200K, 80K, it's many seconds. Many, not milli, many seconds. Okay.
Okay, thank you again, Ori.
Okay, thank you very much.